Now, the last bit that I have to do, I claim, in order to figure this out, is the circumference. And the reason for that is that if I think of this thing as like this tube or piece of paper here, in order to figure out how much stuff there is here, all I have to do is unfold it. Its size, the whole quantity of paper here is the same, whether it's rolled up like this or whether it's stretched out. So if I unwrap it, it looks like what? Well, it looks like a kind of a slab, right? It looks like just a slab like this. And again, the thickness is dx. The height is a minus y. And now we can see that the length here is all the way around. It's the circumference. All right? So this is going to be the circumference when I unwrap it. And in order to figure out the circumference, I need to figure out the radius. So the radius is, on this diagram, is right over there. This is the radius. And that distance is x. So this length here is x, and so this circumference is 2 pi x. And this height is still a minus y, sorry. And the thickness is still dx. Right? All right, so in total, we're just going to multiply these numbers together to get the total volume. We have, in other words, dV is equal to the product of the 2 pi x dimension, the a minus y dimension, and the dx dimension. Incidentally, dimensional analysis is very useful and important in these problems. You can see that there are 3 lengths being multiplied together, so we'll get a volume in the end, something cubic. And we will be coming back to that because it's a quite subtle issue sometimes. All right, so here's the formula, and let's simplify it a little bit. We have 2 pi x times, remember, first I have to substitute, otherwise I'm never going to be able to integrate. And then I rewrite that as 2 pi ax minus x squared, whoops, x cubed dx. Better not get that wrong. And now the last little bit here that I had better be careful about in order to figure out what the total volume is the limits. So the volume is going to be the integral of this quantity, 2 pi ax minus x cubed dx. And now I have to pay attention to what the limits are. Now, here you have to be careful. X is possibly you have to always go back to the 2D diagram. I went to it immediately, but that's the whole point, is that everything gets read off from this diagram here. When you take this guy and you sweep it around, you take care of everything that's to the left. So we only have to count what's to the right. We don't have to count anything over here because it's taken care of when we sweep around. So the starting place is going to be x equals 0. That's where we start. And where we end is the farthest rightmost spot for x, which is down here. Now you've got to watch out about where that is. In the y variable, it's up at y equals a, but in the x variable, we can see that it's what? It's the square root of a. All right, so these limits, this is where you're going to focus all your attention on the integrand and getting it just right, and then you're going to lose your steam and not pay attention to the limits. They're equally important. You have no hope of getting the right answer without getting the limits right. Right, so this is the integral from 0 to square root of a. Again, that's just because y equals a and y equals x squared implies x equals square root a. That's that upper limit there. And now we're ready to carry out this, to evaluate this integral. So we get 2 pi ax, that's pi ax squared. Now maybe I'll leave the 2's in there. 2 pi ax squared is the antiderivative of this, ax squared over 2. And then here x to the 4th over 4, evaluated at 0 and square root of a. And finally, let's see, what is that? That's 2 pi times a squared over 2 minus a squared over 4, which is a total of a 4th, right? 2 pi times a squared over 4, which is pi over 2 a squared.